looking good. Hello, everyone. Welcome to the Types 2 session. As with every session at this POPL, we're aiming for about 17 minutes for talks and 3 minutes for questions for a 20-minute total time. We're going to start off with Orpheas presenting affect, or effect, an affine type and effect system.
Yes, hello. Yes, my name is Orpheas van Rooij, and today I'll be presenting you indeed an affine type and effect system, which we call effect. And this work has been done in collaboration with Robbert Krebbers. So the problem we are facing is that when we have a language with ML-style references and we have also multi-shot effects, these two features can cause problems when put together. And this is particularly a problem in languages such as OCaml. And our solution is to introduce affine types to an effect system in a way that distinguishes between effects that are one-shot and multi-shot. And to make the system more expressive, we incorporate ideas from Russell type and Wadler's use types. And we have formalized the language as a proof of concept, which we call the language we call as affect in Iris and Rock. And we have mechanically proven type safety for it. So before I go deeper into the problem, let me give you a quick introduction into effects and handlers. So firstly, effects need to come from somewhere, and they come from the so-called operations, which you can think of them as just syntactic entities. So for instance, here choose takes a unit and returns a Boolean. And we can use choose to define this effectful function uno, which allocates a reference r with the value true, simply performs the effects choose, and the response from the effect, it puts it back to the reference, and then it just reads back what we just stored on the reference. And here you can notice that on the function type, you also annotate the effect that the function produces. And this is because choose is really, as I mentioned, is a syntactic entity. It has no intrinsic semantics to it. And to give semantics to choose, we have to install a handler for it. So let's do that. For instance, we can choose to always respond to false whenever we get a call to choose. And to do this, we install a so-called effect handler, which you can think of that's kind of like a generalization of an exception handler, where it also takes an extra argument, an extra continuation, which you can see this K, this continuation, which gives you a way to respond back for the handler to communicate with the effectful program that it handles. For instance, when we apply choose false to uno, the example from before, the continuation K really represents what the part of the expression that comes after the effect call. So really what you see here, the part of the expression that's surrounded by this dashed lines. And the argument that we apply K to, K false, is put in this whole of this continuation. It replaces the to choose operation. So really it gives the ability for the handler to communicate back to the expression. I also want to note here that choose false is a one-shot handler because it calls its continuations at most once, exactly once in this case. Alternatively, we can collect all the possible evaluations of the effectful program. To do this, we install a different kind of handler where we call the continuation with both Boolean values and we collect all the possible results in a list. And I'm not going to go into details how exactly this handler works. But the main intuition here is when we call collect all with uno, we will get a list of false and true. Because all that uno does is really just calls the effect, stores it back to the reference, and then just loads it back. And here, collect all is what we call a multi-shot handler, because it calls its continuation more than once, exactly two in this case. So now that we are experts in effects and handlers, let me go a bit deeper into what the problem is. And we outlined two problems. The first problem is concerning the implementations. And the problem with multi-shot effects, specifically when we have the continuations of multi-shot effects, is that whenever we call them, we have to copy again the whole continuation closure of it, because it might be still callable in the future, so we have to somehow need to keep track still the structure. So essentially, multi-shot continuations are quite inefficient to implement. And also, the second problem is regarding optimizations. The problem here is when we have expressions that perform that use references and also perform multi-shot effects. Now, many common compiler optimizations that you can do on such kind of expressions are not sound. And this is particularly a problem in languages like OCaml. And their solution for that is basically to forbid multi-shot effects altogether by throwing a runtime error. But we think that this is not a satisfying solution, firstly because they don't statically track it, that distract that multi-shot effects are being used, and also that multi-shot effects are quite useful also. So let me give you an example, first of all, of an unsound optimization. So for instance, consider this extension of UNO and call it duo. And all that duo does is basically, instead of just calling the choose effect and then store it directly back in the reference, as UNO does, we call the response of the effect, we apply it with the logical AND operation with the value of the reference. And notice that we can apply some simple optimizations to this. So for instance, we can propagate the initialization value of the reference, true. And then we can eliminate the logical AND operation, true, because it really doesn't do much. So essentially, what we have done is we have optimized duo into UNO. And in the one-shot case, so if choose is only handled by a one-shot handler, this is perfectly fine optimization, it's sound. But in the multi-shot case, it's actually unsound. And for instance, if we call collect all, the multi-shot handler from before, we call it with collect all duo, we actually get evaluate to a list of false false. Whereas if you recall, when we called collect all UNO, we got a list of false true. So the semantics are not preserved, essentially. And the reason for this is that because of references, because we also have references in the mix, a call to continuation is somehow it's aware, it can know whether it has been called in the past, much like in what happens in the Groundhog film, if you know the film. But the point here is that when, for instance, in the example of the collect all handler, the first call of the continuation with k false, what happens is we apply the logical AND operation with true. And this is, at this point, optimization is fine. So we are all good. But on the second, when we do the second call to the continuation with k true, what is supposed to happen in the duo is apply the logical AND operation with false. So here is where this optimization really is unsound, it breaks. So the point here is that with multi-shot effects, this optimization is not sound. And we want somehow the compiler to stop it from applying such kind of optimization. And our solution is simply to give more information to the compiler. Specifically, we develop an affine type and effect system, a way that distinguishes between effects that are one-shot or multi-shot. So for instance, choose can either be given a one-shot effect signature, which we denote using this double lolly. So if we give it a one-shot signature, means it can only be handled by one-shot handlers. Or we can give it a multi-shot signature using this double arrow. And by distinguishing between one-shot and multi-shot effects, we are able to address the two problems that I've just mentioned. First of all, regarding copying, that if we have one-shot effects, the continuations of one-shot effects, they don't need to be, they can just apply a destructive resumption on them, because we know that they're not going to be called in the future, so we avoid expensive copies. So we get some kind of benefits from tracking this information. And regarding the optimization, now the compiler has more effect type, knows more information about what kind of effects the expression performs. They're called one-shot or multi-shot effects. And so it can know what kind of optimizations to apply. So, and the language that we consider for this system is the language with effect handlers, with ML-style references and affineness. And this combination of features hasn't been studied before in the context of substructural effect systems. And I'll now show you that this combination brings some challenges. So what are these challenges? The first two challenges are regarding the expressivity of the system. The first problem is that it is a common pattern for many effect libraries that also make use of references to actually store one-shot continuation or continuations into the references, which is a little bit of a problem because references are used to share data, but at the same time also want to store affine data in them. So how can we do this in a sound way? Second problem is regarding polymorphism. If we have some usual form polymorphism over types and effects, an unbounded form polymorphism, this is actually unsound in such a system, that we consider, because of the way affine data interact with multi-shot effects. So how can we still have some kind of polymorphic types in the system while still being sound? And lastly, how can we ensure that all these features of the language interact nicely together? So specifically, how can we prove type safety, but not just regular type safety, but also that the usage guarantees, for instance, of one-shot continuations are obeyed? And our contributions address these problems exactly. We're inspired by a Rust cell type, and we have our references are shareable regardless of if they store affine data or not. We employ a form of bounded polymorphism by extending Wadler's use type to effects. We take a semantic type soundness approach to prove type safety that also incorporates the one-shot guarantees. And lastly, we have more or less the whole language. In Iris, we have mechanically proven type safety, and we call this language we call affect. So let me go a bit into zoom into the contributions. So first of all, we have our cell-like references. And the challenge here is that if we naively just combine references that are shareable, but at the same time also store affine data, well, it wouldn't be very sound because we can just get an affine value, store it behind the reference, share the reference, and we can get the value twice from every alias of the reference. So we need some kind of a restriction of the operations of the reference. And our solution is to use a cell-like inspired API. So the operation that we can do on the references, we can only load for the reference from a reference if the value that the reference stores is of an unrestricted type, in contrast to an affine type. And if you want to deal with affine data, we use this replace operation, which simply just acts like a store on a reference, but also returns the previous value of the reference. So the replace allows us to deal with affine data because the concept is very simple. Essentially, whenever we want to get the affine data back from a reference, we have to store something back. And the observation here is that many challenging examples from effect literature, such as a library for cooperative concurrency, that heavily relies on storing one-shot continuations into references. It can be easily adapted, and we have adapted it and have type checked it in effect, and by using this replace operation. So we can ensure that the one-shot guarantees are not broken. The second contribution is regarding polymorphism. I have said that we use a form of bounded polymorphism in the form of use types. But let me give you an idea of what the problem is here. So consider this small example called foo, which is just an abstraction that performs the effect choose and then returns its argument. And the question here is whether we can be polymorphic over the argument type while still give choose mark choose as a multi-shot effect. You can see here with the double arrow. And the answer is no. It's unsound, because if we call foo with some affine function, which is the affine function is v in this case, then this affine function will be captured in the continuation of the effect. And this is a very bad thing. We really should forbid this. So capturing affine data in multi-shot continuations breaks all the soundness, because we can easily get this affine function twice by just installing a multi-shot handler on the expression. So in actuality, there are only two sound possibilities to give to this effect. The one possibility is to allow any kind of argument type, but restrict choose to be a one-shot effect, which you can see here from this double lolly. Or we can be polymorphic only over unrestricted types, which we express using this bang type former on alpha, which is inspired by the bang type from linear logic. But then in that case, if we are polymorphic over unrestricted types, we can have choose as a multi-shot effect. So the challenge here is how can we express both of these two possibilities in one type signature? And to this end, we introduce a dual to the bang type former, which we call the flip bang effect former, and incorporate this into a Wadler's use type kind of form. So we introduce a novel effect former, which works on effects, and we quantify this bang, and in our case, the flip bang, over variables, just like what happens with the use types. So here, new ranges over once and multi, and for every instantiation of the two actually gives us one of these two possibilities. For more detail how this works, you can see the paper. Lastly, I want to say a few things about how we prove type safety. And specifically, what we want to show is not just regular type safety in some like no usual type errors, but we also want to show that our one-shot continuations are really called at most once. And it's this combination of wanting to guarantee that one-shot continuations are called at most once, and having these cell-like references, where we share, our references are shareable, regardless if they store affine data. This is what makes syntactic type soundness approaches it's less clear how they can be used, at least, in this case. So instead, we take a semantic type soundness approach. And to do this, essentially what happens in a semantic typing setting is that we interpret our typing judgments, our effects, our types into some kind of semantic domain, which in our case is the separation logic of iris. So we build a logical relation in iris. And the main idea is that you have to prove two theorems. Firstly, the fundamental theorem, which relates the syntactic typing judgments to a semantic typing judgment. And what happens here is because semantic typing judgments are really just iris propositions, so they're propositions in our logic, what we have to show, actually, is that every typing rule becomes a lemma that we have to prove. And in the adequacy theorem, we have to somehow show that semantic typing judgment really implies expression safety. So I have mentioned that in the semantic setting, each typing rule actually becomes a lemma. But to prove this kind of semantic typing rules, we have to somehow be able to reason about programs written in effect. And to this end, we use the program logic of De Villiers and Potier from POPL'25, which allows us to reason about programs with effects in iris. And we extend it to work for programs, to reason about programs in effect by introducing effect rows and also by unify the reasoning about one-shot and multi-shot effects. And this is the end of my talk. Here you can see the contributions again. We have expressive references. We employ a form of bounded polymorphism. And to prove the meta theory, to prove type safety, we built a logical relation, separation of iris. And this whole thing has been formalized in iris and rock. Thank you.
We have time for a few questions. I already see one from Ralph.
Yes, thanks for the nice talk.
Hello.
So I was wondering, in what you mentioned about the optimizations, right? So, okay, if I now have this do choose thing right there, and like I can see choose is a multi-shot thing, I stop doing the optimization. That's nice. But now, what if this is hidden inside a function call, right? Like I could call a function which triggers a multi-call optimization, multi-shot continuation, and the optimization is just as unsound because this is like a function that returns multiple times, which is weird. Yeah. So how do you track that?
Well, I mean, so somehow the effect system tracks any kind of effects they produce, and regardless if it comes directly from a do construct or it comes is hidden behind an abstraction. So that's why, if I understand correctly what you mean, by the function type is annotated by the effects it produces.
Yeah. Okay, that makes sense. So it's not about whether the function does. Okay. Yeah. Okay. I think I get it. Thanks.
More questions? Right here.
Hi, thanks for the talk. This is really cool stuff. I was wondering if, I don't know if you ever said anything about it explicitly, but are there any, is there any performance that you leave on the table by supporting multi-shot continuations alongside one-shot continuations? Are there any things that if you were to do this and only focus on one-shot continuations that you would change, mostly for performance?
It may not be clear here, but there's no implementation involved in this work. It's just a formalized language in Rock. So the whole idea, the whole concept behind motivation, behind optimization, everything are just statements that that are plausible statements on how they can be used. But it's all of like future, how one could use it, not how currently it is. But specifically about your case, I guess that would be a lot implementation specific, but I think not, to be honest, but without giving any concrete presentation. I think it's also implementation specific.
All right, I will ask one last question while the next speaker gets set up. And my question is also somewhere expressiveness related. OCaml has a letrec construct, which I don't think your formalized language has.
It has.
Oh, it does have.
Well, not specifically in the form of letrec, but, well, actually, no, it's a...
So what happens if I write letrec x equals replace label with x?
I let rec, sorry, what is it again? Let rec.
So the replace function
Uh-huh.
takes an argument which is going to be the new thing, and it returns a value which is currently there. If I combine that with the let rec combinator, so I let rec x, which will eventually be the value there, equals replace some container cell with x itself. It seems like the fixed point for that is x is the thing that is in there, and that is still in there.
All right, okay, so in terms of let rec being that, yeah, I mean, this is a call by value setting. So basically, you would just be calling the replace all the time. Well, yeah, you actually would just be calling let rec all the time. You wouldn't even call the operation because it's called by value. So you wouldn't even be calling the replace because you call x. You've tried to evaluate x, and then you go into this loop, if I understand correctly.
Okay, that makes sense.
Yep.
Great, let's thank the speaker one last time.